So hi, everybody, and thank you for the introduction. Like Jonathan was saying, I'm here to talk about pragmatic implementations of the digital thread. So for those of you who missed my introduction earlier, my name is Melissa Harvey. I'm with the Boeing company and have been for 13 years. Prior to coming for Boeing, I was a wee little entry-level drafter in the mechanical space, and I worked for a firm out of Houston, and I did HVAC drafting, and I worked on, like the UT campus at San Antonio, and I did some riser diagrams and other entry-level things for, the SeaWorld Research Center and stuff before I came out to Boeing. When I came out to Boeing, I spent the early part of my career focusing on model-based definition tools for the mechanics on the shop floor. How do we get them the MBD data tailored to what they need so they can execute their jobs, and how can we facilitate that in the most cost-effective way for the company? I spent around 5 or 6 years in that space, touching on different elements of it before I moved down the process stream into supplier distribution for the model-based definition. And that really focused around the tools and system of systems that we had in place to automate the distribution of model-based definition packages to partners and suppliers based on what their contracts were for their work packages. From there, I moved into the space of industry data standards, and I've been there around 3, maybe 4 years at this point. And it's been a real growth experience for me, and it's been so technically interesting, focusing around maturing the data exchange methods that we have, specifically focusing on ISO 10303. And I started out focusing on AP 242, which is the industry data standard for model-based definition. And then I slowly just kind of kept getting pulled back into the manufacturing space because I can't help it. I'm just interested in the application of what we're designing. And so I've been working to grow in that area and specializing in the application for standards to help facilitate manufacturing automation. And so it's been leveraging my MBD knowledge and that knowledge of AP 242 and then pulling it into the AP 238 space, which is the standard and protocol for our manufacturing data and our manufacturing processes that pulls in the needed elements from the MBD and then supplements them with the additional manufacturing elements and manufacturing processes. Down below, I have a master's that I graduated with earlier this year in information systems, and my initial degree was in computer drafting and design, and I have a few certificates where my interests have just kind of pulled me where I've wanted to kind of fill in some gaps that I've had around systems engineering and around additive manufacturing. So what I'm here to talk about today is really around the concept of the digital enterprise and the digital twin, which there's been a lot of excitement about over the last so many years. And I think we're all kind of rallying around the fact that we do see opportunity in the digital enterprise and the digital twin. But when we have the idea that we want to go forward and do this, there's a long way between where we are and fully realizing that goal, I think, across all of our industries. And the glaring truth is we're trying to march towards that end goal. One of the roadblocks that we're running into in the manufacturing space is a lot of the tooling and a lot of the machining that we're working with and that we have millions of dollars invested in was not designed to integrate with the digital thread. And we really have to think outside of the box here and say, how can we find interim solutions so we can get value now with machines we have and still keep marching forward to the digital twin? Because it's not very practical that we would all go out and replace all of our machining at this point. And we do need to find a pragmatic way to make it work, so we can get to the goals that we want. Okay. So I kind of plan just to talk about the why, what, where, when, how of all of this. And so I'm going to go into initially kind of what is the driving force for us moving to the digital twin. Why do we care? And from there, I want to level set when we're talking about the digital twin or the digital twin framework. Let's level set on what we mean there, because there are a lot of definitions out there. And I just kind of want to bring us in context of this presentation. These are the things that we mean. Then I want to go into what we're talking about with the digital twin framework in application. What does that current flow look like? What does the ideal flow look like? And then get into what I consider the fun part of this presentation, which is where we take a look at some of the actual implementation where we've found ways to get the digital twin to connect together in specific manufacturing use cases. So let's go ahead and dive into it. Okay. You know, I've been with Boeing for 13 years, and that's not nothing, but it's also, you know, not a long time either. The one thing that I've kind of really learned over the last 5 years, and I think everybody on this call can agree with, is that business changes. The managers we have change, our business goals and objectives change as our leadership changes. And we certainly, at a very high level, need to be adaptable as businesses in our industry so that we can stay competitive. And so as we've, you know, the company I'm with, we've been around over 100 years, and we really have had to adapt how we do business so that we can stay competitive. That is the driving force for the change. And that's no different when it comes to the digital thread. So, you know, back in the beginning when we were doing hand drawings and we moved to doing digital drawings, that at the time was a huge investment from the company to, you know, invest in the computer systems, to change all of our processes, to go through and to train our people to be able to adapt to that difference in work. And, you know, the advantage really there was we were able to get efficiencies. We were able to be able to help the productivity of our workers, increase our quality. And then when we moved from 2D computer-based drawings as MBD and CAD evolved, and we moved to our programs taking on model-based design as opposed to 2D drawing design, that was, again, it was years in the making for us to make that transition, because it was an investment cost to change how we did business. But ultimately, the return on investment was there for us to drive to that change. You know, it's really what's enabled us to have global collaboration. We've had increased in quality designs for spatial integration. And again, this isn't just a my company thing. This is across, you know, the many industries who've made this transition to full model-based definition designs. And the driving factor as we move into this realm of the digital enterprise and the subcomponent of that being the digital thread is we really have a driving factor, okay? And it's the business benefit that we can get from this transition. So now the question that I was hoping to lead you guys all to be asking at this point essentially is, okay, well, what is that benefit and what are we talking about when we're talking about the digital thread here? Okay. So to baseline, because there are a lot of definitions out there, and we have several external groups that are really making progress to narrowing us down to the one definition to rule them all. But while we're making progress, we're not quite there. So just for context of this presentation, is simply put as we can have it. When I'm referring to the digital thread, I'm talking about disbanding the silos that we have around our data. We're connecting our data, we're connecting, meaning our information, our processes, our people, our machines. So all of our data is being connected, and it's through the entirety of our business. That includes internally and externally. And then the last element here is through the entire life cycle. And so, you know, no silos, connecting all of our information processes, people, and machines for the entire company and across the entire life cycle. Okay. And the benefits to that, I mean, and there are really a ton of them, but in my opinion, you know, there are some real heavy hitters there, and it's the ability to picture our business end to end. And in that, it allows us to leverage all of the information and data we already have and pivot it for analytics to allow us to make informed decisions. And with the speed of data analytics through automation, we can really increase the rate at which we're able to get that necessary information, so we can be ever more responsive and adaptable to the things that we need to in a business. And as culturally we're adjusting and really expecting quicker and quicker and quicker turnaround and quicker data, the same thing is true for the demand on our business. So the rate at which we're evolving and expected to adapt to these changes is shortening. The cycle is becoming quicker and quicker. Whereas in the past, the evolution from, 2D drawings to MBD, we were able to take a decade, 15 years. Now, the demand that we adapt to this concept of a digital thread and a digital enterprise is for shortening. Okay? So while high in the clouds, we talk about, oh, well, we're going to unfracture our data and connect it all together. It really comes down to a framework. And that framework for the digital thread is essentially asking the question of, given the network we're in, because networks are the backbone of our digital enterprises, given the network we're in, what information do we need to connect and how do we connect it? Okay? And like any framework, that's really going to be dependent on a lot of subcomponents. And related to the digital twin, that's going to be the subcomponents of your user, or not your user, that's just one of them, but of your network. And so I'm not going to go into great detail on this slide. I really just wanted to show that based on the network that you're in, the answer to what information you're connecting and how you're connecting varies greatly. Okay? And if anyone wants to get together and have a deeper conversation around this, we totally can. But for now, that's just the main point that I'm trying to get across, is the network really drives how you're connecting your data to achieve that digital thread. So we've answered why we care about this. We've kind of talked about what it is at a high level. Now let's get to the interesting part, where we're really talking about how does this look in real life. So the use case that I want us to go through is the dynamic scheduling of robots. So this is a pictorial view of what we're talking about for the flow of data in a digital thread around the robotics and feeding the robotics the information they need. So let's walk through this a little bit. So essentially what we're talking about in this view here is that we have our PLM, ERP, and MOM data. And that data, and this isn't an ideal world, that data, as soon as it triggers approval, it's flowing into our user entity. And our user entity is going to be responsible for a couple things. It's going to be responsible for consuming that source data, and it's going to convert it into work plans. And those work plans are going to be the jobs that we have for the robots. Okay, the other thing that we're going to do up here is they're going to schedule that work in what order it needs to be executed on what machines and all those sorts of things. Then once that is submitted, it's going to auto trigger and get fed down to a device control, which is going to feed that information into the robots themselves. And the robots are then going to receive what their work statement is. And when they're told that they're all ready to start, they're going to execute that work. Okay? And then in an ideal state, what we're wanting to happen here is in real time, these robots are going to send the information back upstream to be reconciled into the digital twin. And that information, I mean, it can be any number of things. It's going to tell us how they're executing their work, where in the parameters of where a hole can be drilled, what it was actually drilled to, kind of in that goalpost that we set from the CAD design. And if there are any hiccups or problems, it's going to tell us where it ran into them. And we're even going to give it the capacity that we have sensors in place. And when we, say for some reason a part is unreconcilable, we blow the hole out too big, it's going to be able to stop the operation. And based on the parameters that we tell it, it's going to be able to make the decision, this part can be reconciled and we need to keep work on the other areas, or this part is completely ruined. We're not going to waste our machining time anymore on it, and we're going to stop all jobs. And it's going to have the ability to make those decisions based on how we tell it to make those decisions. And all of that information, again, is keep flowing up, and it's going to maintain the integrity of where the physical twin is at in relation to the digital twin to complete that data flow. And that's going to be the information on the actual physical part, as well as the execution of the processes that it was sent. Okay? So that looks easy, right? Everything just talks to each other. But as we all know, it's not actually entirely easy. So at the top part of this, we're talking about systems interacting with systems. And, we're not perfect here, but we have really good progress on how to do that and how to facilitate that flow of information between our modern systems. We do it with industry data standards, and it's fairly there, okay? Where we're really running into the roadblocks in the manufacturing world in this type of use case is taking this modern data and having it consumed into our robots, into our machining, plug and play whatever machine you want to put down here. And the reality is when we're out on the factory floor, a lot of these, like we said earlier, weren't designed to integrate into the digital thread. The reality is that majority of our manufacturing machining is talking in I don't want to say outdated. It's talking in older protocols. So a lot of these machines talk in G code, and that's something that was written in the 1960s and is really limited by what the constructs were at that time and the forms and structure of data at that time. So while our business processes and our design practices have moved forward for the last 60 years now, something like that, the code that we communicate into these machines hasn't changed. And it's a very limiting factor when we're talking about giving them all this new information. And it's a huge roadblock in trying to get that information communicated back out of the robot so that we can feed it back in to complete this loop of the digital thread. Okay. So this is where I think it gets fun. So like I said earlier, up here, systems talking to the systems, we have a clue how to do that. We're doing pretty good. We're facilitating it with our data standards, and we're having success there. The problem is down here. And so this is where we got really practical with it. And not, a larger group of people is who I'm referring to in the we. got together and said, okay, how can we make this work with what we have? Because that's really what this presentation is about, and that's how we get incremental value until we reach our end goal, is really how do we make it work, okay? And how we're doing that is by saying, if the equipment has to talk in G code, how can we get the information we have from the format it's in, AP238, into G code format? And so what has come up with is taking third-party optimizers and developing this concept of enhanced G code, where we work inside of the constructs and the organization of G code itself, but we get creative with it to be able to bake in the sequencing and new information we have from, the CAD information, as well as the manufacturing information. And I'll show us an example of what that enhanced G code looks like in a little bit. In this specific context, rapid is a form of G code, and enhanced rapid is what we're referring to for the enhanced G code in this application. And so that's allowing us to get these work plans with all the additional rich information into the robots. And then the robots read them because they know how to read that, and they execute their work. And then the other end of this is, okay, we got the information in, the robots are doing the work. Now, how do we get the information out so we can close that digital twin loop? And we're doing that with something called, in this use, MT Connect. And MT Connect is it's a communication hub that's allowing us to extract the real-time information from the robotics and convert them in so they can be stored in or internalized into our system and consumed upstream into the process and the process digital twin and the physical twin of the digital. And in this instance, we're talking about OPC UA. Okay. So just to recap where we're at a little bit, if we're talking about a pragmatic solution, we have building blocks, and the building blocks are allowing us to get the value we need with the machines that we have. The first building block is allowing our data to flow through our systems, and we're leveraging 242 for our CAD data. We're using 238 for the elements we need to bring into the manufacturing space. We're leveraging a digital twin framework, which ISO 23247 is the standard that will outline the digital twin framework, and it will tell you by your network how to answer that question. What is the information we need, and how do we connect it in this type of network? Because that's the backbone, okay? And then we're using third-party optimizers to convert from the modern format and output this enhanced G code so that we can get the information into the machines, and the machines can do their good work. And then we have MT Connect, which we're standing on to help flow that information back from the machines and get it back into our digital twin. Okay. And so, boop. This is what I promised earlier, where I was saying we were going to look at a form of G code. And so if we're looking at this, the black this is the format that it's used to expecting information in. And the blue part is where we're enhancing it. So we're working with the existing construct of the G code, and we're essentially tagging. And that tagging is allowing us to bake in all of this additional information for work plans so the robots can receive it. And this wouldn't typically be in G code. And G code wouldn't typically expect to have all of this additional information. But again, working with those third-party optimizers, we've asked the question, what information is missing from the G code that we need to get in there? okay? How can we work within the construct of the G code that the robots can understand to get this information into there? Okay. And so that's the building blocks that we're working on to achieve the digital twin right now. And the next thing I want to go into, so that was kind of a theoretical use case. I want to go into where we've taken that and we've actually executed it in real life. And so a joint venture between Boeing, University of Washington, and some other folks, we got together to take that dynamic scheduling of robots and actually execute it. And this is cool stuff, guys. So there is a robotics cell inside of the BARC Collaboration Center. And what they've done is they've set up a part of a wing, and we've simulated a drill and fill operation with 4 robots. So typically in the real world, most of our drill and fill is very much a human operation. And so what do we know about humans? We're pretty flexible. We can think on our feet. We're adaptable, but, you know, we're pretty fragile. And there's long-term repercussions of trying to fit into some of these spaces to be able to achieve these drill and fills. And what do we know about robots? Well, robots are really sturdy. They're not going to break the way humans break. They're not going to complain that their back hurts and that kind of stuff, though they might output a maintenance error code, but we can work with that. But the difficult thing with robots is they're not mentally as flexible as humans. So that was really what we needed to overcome and what we still need to branch out and build on. And so this is where the digital twin comes in and really helps us give the tailored information to the robots so that they can be flexible, so that they can have all those bits of data that they say, if this happens, what do I do now? What information do I need to do that? Oh, that's over here. Okay. And so a little bit more context here. These 4 robots are ABB 120 model robots, and we had 4 of them. Okay. And so this is kind of more of a 23247 view, a digital twin framework view of that same example that we showed up here. It's just allowing us to see it in context of a proximity network. But we do still have our cell collector. We do still have our hub here, which sends our work plans to the robots, and we have our NT Connect agent for the robots to send the information back to complete the digital twin. And so what's interesting here is when they applied this, they sent work plans in, and the robots, each of them have different build envelopes, and they reconciled what their work was for each of them. And, you know, they happily started working along. But what's kind of funny what they did is they intentionally sent commands to one of the robots that it was not able to execute. I can't remember if it was outside of its build envelope or it forced it to have some kind of conflict. But they were testing to see, one, can the robots receive the information? Can they execute their jobs and send it up? And yes, they were able to do that. But what they were also testing is if it runs into a conflict, can it figure out what to do next? And in this instance, the correct action for it to do was to stop working. And it actually did. And so the machine stopped, pulled off to the side like it was supposed to, and then it sent the information back upstream to say where it was at in its process, what error it received, why it couldn't proceed, and it sent the physical twin information to let that be updated to also say, you know, this job wasn't executed in the physical twin. And that was everything that we could have asked it to do. Okay. So what do we learn from kind of all of these pragmatic implementations? And it really is that the equipment wasn't designed to work in this digital enterprise space. So we do need to come up with ways to make it work for right now, and we can, right? But it's all about balancing that investment cost as we march towards realizing the full digital enterprise. And industry data standards offer a way to carry the data, but they carry the data very well through our system of systems. They do not carry the data very well into our robotics and our machining, because again, the machining just doesn't talk that same language. But that doesn't mean we're fish out of water here. We can still make it work through third-party optimizers that are really allowing us to convert that data so it can be read and received. And then also through third-party applications like MT Connect, which allow us to bridge that data back up into the digital thread. And so last takeaway really is we're still doing work here. We're still pushing additional use cases and growing, and we need all the help that we can get. This is work that's being done inside of ISO WG12. So ISO TC 184 SC4 WG, or sorry, not 12, I'm sorry. I'm still on that MBD track. No, it's WG 15. And you should reach out to your representatives. It's really, really interesting work. And so my last slide here, I just wanted to give a great big thanks, because like I said, when I'm talking about the we, this is a great big group of, really, really awesome thinkers that I'm just glad to be able to interface with. And so I'd like to open it up if anyone has any questions at this point.
Great, Melissa, thank you. Yes, there is a question here. Let me read it off to you. The digital thread is a great concept. However, we have airframes that are 70 years old where there is a limited amount of money to convert from drawing to digital. Likewise, based on our cycles, these airframes are no longer per drawing, and the parts required to keep them airworthy are literally designed for integration by the installer at the point of use. How do you see this issue overcome?
So I'll give you my answer from the perspective of I'm very much a realist. I think that each of us as companies need to take a look and see what is the value proposition for making these transitions. And practically speaking, that return on investment isn't always going to be there. There's going to be some instances where the cost of converting doesn't have enough value to justify it. And so I think we're going to be running this parallel path for some time, where we do maintain old technology until it just naturally kind of retires and goes out, because there's no value in doing that conversion. But that doesn't mean that we can't go forward with the places it does make sense. And that all really comes down to analytics. We need to understand the information we have and leverage it to make those decisions for ourselves. Did that answer your question?
I think so. That question was from Todd Downer. Todd, do you have any other remarks towards that? If you're still on the call.
Well, thank you so much, Todd. If you, oh, did they come in?
No, go ahead, Melissa.
Okay, I was just going to say, if you think of anything else or want to have continued chat, feel free and reach out, and we can talk offline as well.
Yes, so Todd did answer. He's yes, good answer, and likewise, it points to the fact that that MBD is not a peanut butter spread across all of commodities. Great. Okay, let's see. If there's any other questions, please feel free to write them on the panel box and we can address them. By the way, Melissa, great presentation, very informative.
Thank you so much. Yeah, I had considerable help from Dave Odendahl, so I just wanted to give him a shout out for helping me validate and build the presentation so that I didn't make a fool of myself.